Okay, welcome. Let's talk about matrix operations. So I'm going to do a couple of basic matrix operations. The first one is the way we denote and talk about matrices. So anytime we have a matrix A, okay, we're going to talk about a matrix A having a certain number of rows and columns. And that's the way generally that we're going to refer to them and write and work with them. Sorry, move that out of the way. So that's the way we're going to work with them is rows and columns. So usually we would say like matrix A is a 2 by 3 matrix. Now the other thing is we want to be able to note the elements in a matrix very quickly and with consistency. So one of the things we'll do is we'll denote each element by its row and column. So I'll use something like A1 1, row 1, column 1, A1 2, row 1, column 2, A1 3, row 1, column 3, and on. So we can describe matrices and their elements very, very quickly. So if I had another matrix, which may be a B 2 by 2, that one would be perhaps B11, B12, B22, B21, that sort of thing. Now we will do specific matrices, so we can talk about a matrix really specific, and we just, in that case, would simply write out the matrix. So matrix 2, 3, 5, 7 would be simply the matrix written out like that. So the first operation we're going to do is a scalar multiplication. So the scalar multiplication of a matrix might look like something like, for example, 2 times matrix A. And that is simply going to be 2 times each element of the matrix. So we just simply distribute the scalar throughout, just like, for example, distributing it through a bracket. So in that case, we would get 4 as the first element, 2 times 3 is 6, 2 times 5, 10, and 2 times 7, 14. Okay, this is 2a. In general, Ka would be exactly that. So if A was a 2 by 2 matrix, sorry, that would be A11, A21, A212, and A22. And in general, if I use k as an element of real numbers, then I can actually define this in a very pedantic way as k times a is simply going to be k a11, k times a21, sorry, a12. These are backwards. I'm sorry. Messy. This would be k a21 and k a22. I'm sorry. Make sure you change those two here. So that would be my Ka. And notice that I could flip that around and write that as Ak because each of these can be flipped around to A11 times K. So I can move right, multiply scalar right or left, right or left. Now that's not going to always be the case. In fact, with multiplication, left and right multiplication is going to be very different. The next step might be adding two matrices, so we'll go ahead and do that. When you add two matrices, we're going to be really specific about adding two matrices. They have to be adding matrices of exactly the same size. And that will work for add or subtract. So if you add or subtract A plus B or B minus A, something like that, okay, A and B must be exactly the same size because we're going to define it in the following way. So I'll do it for A, for example, and B, both 2 by 2. And I'll use the same denotation that I had up above. So A 2 by 2 would be A11, A12, A21, A22. B would be B11, B12, B21, B22. So when we add two matrices, we add all of the corresponding entries in each column and row. So it would be A11 plus B11, A12 plus B12, A21 plus B21, and then A22 plus B22. Okay? Then we get A plus B. This is our definition of A plus B. Notice that if we take these values for example, A11 and B11, these are real numbers, which means that we can move these order and commute B11 and A11. Well, that means we can do that for the entire matrix. So we can write B11 plus A11, B12 plus A12, and then B21 plus A21 and B22 plus A22. A little pedantic, but notice now if we split that up and we reverse what we were doing, we see that's exactly a B plus A. So when we add matrices, this is actually an operation that commutes. So A plus B is equal to B plus A, and that doesn't really matter the size as long as the two matrices are the same size. So I'll actually prove that A plus B equals B plus A, given that A and B are the same size. So we'll say A and B are both matrices, and now I'm going to open it up to any finite size matrix n by m. So to denote that, I'm going to do a little bit of shorthand, but basically notice that we'll do A11, A12, and this will go all the way to A, and this is an n, so there's m columns. We can go down, there'll be n rows. That means as we go through, this will be like A33 in the middle. And finally, this last entry is ANM. B is going to be exactly the same, B11, I should do this 1M, AN1, and then finally, BN1, BNM. So when we add those two matrices of almost any size, as long as the size is finite, then the corresponding result will be A11 plus B11, A22 plus B22, and then finally A1M plus B1M. That goes throughout, AN1 plus BN1, and finally the last corner, ANM plus BNM. Now remember that property, I'm simplifying here, there's many rows and many columns. So for any n by n, so for any particular ANM plus BNM, that is BNM plus ANM. In other words, I can reverse this entire matrix. So I got AB11 plus A11 all the way down to BNM plus ANM, which really is matrix B plus A. So there's the proof. One of your first proofs in the course is proving that A plus B is B plus A for any NM. It's kind of an interesting result. Subtraction isn't going to be all that different. So A minus B, if, sorry, little pen skill there. So let me do some specific matrices. A is 1, 2, 3, 4, and then B is 6, 7, 9, 8. And now I do minus. All I'm going to do is 1, 2, 3, 4, minus 6, 7, 9, 8. And now I subtract the corresponding. So 1 minus 6, 2 minus 7, 3 minus 9, and then 4 minus 8. And that will give me the matrix -5, -5, 3 minus 9, -6, and then -4. So this one just happens to be negative. It doesn't always happen that way. So A minus B is the same thing as long as it's the same size. We're ready to go. So the next kind of operation, this one is a lot more specific and unique. That is matrix multiplication. So for matrix multiplication, we're going to do a lot of the similar things, except it's really going to be specific. So we'll talk about A being a matrix that has, let's say, let's do R row times columns and B row times columns. So first of all, for matrix A and B to be defined, the inner value, the columns of A, must equal to the rows of B. So the columns of A must equal to the rows of B. The result is going to be row times column. So the rows of A times the columns of B. So that's kind of a little awkward. So let's kind of do this in a specific example and how we actually do this multiplication. So I'll actually do it as an example. A lot of times that works and people understand. So we're going to take A. In this case, we'll be specific. A is going to be 1, 2, 6. Sorry, 1, 2, 4, 2, 6, 0. B is going to be the following matrix: 4, 1, 4, 3, 0, minus 1, 3, 1, and then 2, 7, 5, 2. So this is where we're going to have to be a little neater. When we do A by B, A times B as a matrix multiplication, we're going to be very careful in neatly arranging A to the left and B here to the right. When we multiply matrices, we will see that right versus left is very important. So we are left multiplying A times B. So A on the left, B on the right. Unlike matrix addition, it's not necessarily going to be that AB is equal to BA. This is possible, but it's going to require a really special condition. So when we do this multiplication, we notice that, again, I'm going to check. So I have 2 rows, 3 columns, 3 columns, 3 rows, sorry, 4 columns. And notice the 3's match. This allows me to do the multiplication. We'll see these two match. The rows of A match the columns of B. The result is going to be a 2 by 4. So I'm going to write that here. This is the 2 by 4 resulting. Now, how do I get the 2 by 4? Well, for that, I'm going to actually do 2 rows and 4 columns. I'm going to actually, this time, call that out so we can see what's going on. So how am I going to get these values? Well, in each row, we're going to take the 1 corresponding with the 4, the 2 corresponding with the 0, and the 4 corresponding with the 2, and multiply them. So the first element is going to multiply by the first element. So the first element in the row 1 is going to multiply by the first column element. So that'll be 1 times 4. And then we're going to do second with the second. 2 times 0. And then we're going to do the last one, 4 times 2. So we're going to do that for all of these entries, and if you notice, we're going to have a bunch of these entries. So when I do that, I'm just going to write the result down here. 1 times 4 is going to be 4, plus 0 plus 8 is 12. So that's the first entry. Now we're going to do that for all 8 entries. So let's review it and do it step by step. So up here, we're going to do now the first row times the second column, and exactly the same thing. So it'll be 1 times 1, 2 times minus 1, and then 4 times 7. If we do that, we will get 27. Then we'll do the third row, first row, third column, I should say. So that's 1 times 4, 2 times 3, and then 4 times 5. We add that up, 30. Okay, I'm just going to randomly do one. So the next one would be 13. We did this one. We would do now for the second row. Notice I'm going to go here and arbitrarily pick this value here. This is second row, second column. So to get that, I need to use the second row, which is 2, 6, 0 times the second column, which is 1 minus 1, 7. You can see you could just do that off to the side. That would be 2 times 1, 6 times negative 1, and then 0 times 7. And that would be negative 6, negative 4. And that's what I would put dutifully here. So if I did that piece by piece, I would get 8 minus 4, 26, and 12. So that is A times B. I get the 2 by 3, 3 by 4, and I get a resultant of a 2 by 4. Notice if I try to multiply B times A, even if I check, B, remember, was a 3 by 4, and then I would be trying to multiply that by a 2 by 3. Notice we wouldn't even be able to do that. That is not defined. So in this case, AB can't be equal to BA because the matrices aren't even going to be the same size. They're not even the same size. AB is defined and BA is not. So that is a kind of weird thing about matrices, a weird characteristic. Once again, let's review how we do that. We take the row elements of one row times the column elements of the other matrix, the second matrix, 1 times 4, 2 times 0, 4 times 2, and that's the result we put in row 1 times column 1. That's basically the bottom line of matrix multiplication. It is a little confusing, but that's basically the way to go. If you had a bigger version of this, you could just simply do that mechanically and look for the particular row. So again, if you took this row, row 3, and maybe this column, maybe column 4, you would be actually calculating the element in the third row, 1, 2, 3, and the fourth column. So it would be the third row and fourth column value. That would be the value. And then it would be these values here. So if you had 4 rows, 3, so this would have to be a matching value. So these two would be the same size. So this value, if this had 5 values, this would have to have 5 values. So the number of columns of the first matrix would have to match the number of rows in the second. And the result would be whatever the rows of the first is times the row of the second. Kind of an unusual property, but that's matrix multiplication.